Hey everyone, so today we're going to be doing merge sorted arrays, which is a question from elements of programming interviews in Python. To test our solution, we're going to be using the EPI judge, for which there will be a link in the description. So the question asks us to merge a list of sorted arrays, and we want to return this merge as a union of a sorted array. So we're going to receive a list of sorted arrays such as 3, 5, 7, 0, 6, 0, 6, 28, and we're going to return a long list which is also sorted and combines all the values found in the arrays. So this input would give us an output of 0, 0, 3, 5, 6, 6, 7, 2, 8. Now this is a question that's very easy to solve with weak runtime complexity. However, if we want to get an efficient solution, we're going to have to use some pretty clever problem solving. So a quick brute force method to do this would be to just create a merged array and then sort it. So something like merged equals list, and then for array in sorted arrays merged plus equals array, we can then sort merged and then return merged. This is going to missed an S there. This is going to pass all of our test cases and is going to have a runtime complexity of O of n log n. And this is not bad. I mean, we're essentially just taking a list which contains all the values in our given arrays, and we're simply returning a sorted version of all of them combined. And there's nothing wrong with this. However, we're not really taking advantage of the fact that the arrays within this list are already sorted. So the hint is, I mean, when part of the problem is already done for you, you know that you have to take advantage of this fact somehow. So one thing that we can do is we can use our strategy to merge two sorted lists, so using two pointers into another array, and then we can recursively merge those arrays as well. Another method, which is the method that we're going to be going with, takes advantage of a data structure called a heap. Now, for those of you that aren't familiar with heaps, I'm going to put a link in the description that explains how they work. However, all we need to know for this problem is that heaps are very good at keeping track of whatever the smallest element is. So a heap will pop the smallest element in O of log n, or O of log k in our situation if we have k sorted arrays. So what we want to do is we want to iterate through each one of these lists, keeping track of whatever the smallest value is. And whatever the smallest value is of all the smallest values in all the arrays. So if we look at the smallest value in the first one, the smallest value in the second one, the smallest value in the third one, and then based on those, whatever the smallest value is, we're going to take that value, we're going to put it into our final list, and then we're going to move on to the next value in that array, and then also append it to our heap. So visualizing it for this example, we're going to start with a heap of 0, 0, 3. We're going to pop off the 0, we're going to add it to our result array. Then we're going to append a 6. Then we're going to pop off a 0, we're going to append another 6. We're going to pop off a 3. We're going to add a 4 or add a 5. Each time we're creating this array. So we have 0, 0, 3. Then we're going to get rid of the 5, which comes from the first array. We're going to add a 7 to it. Then we're going to pop off this 6, add it to our array. The second array there is done, so we're not going to append any more values. We're going to pop this 6. We're going to append the next value, which is in the third array. We're going to put 28. And then we're going to pop the 7. We're going to append it to our array. Then we're going to pop the 28, append it to our array. Then we're not going to have anything left in our heap, and we're going to return the final value. Now, since we're only keeping the number of arrays in the heap, and let's say we have k arrays, our final complexity is now going to be, it's going to be n, because we're going to be doing this n times. And each time we're going to pop, it's going to be log of k. So we've substantially reduced our time complexity from n log n to n log k. And this k might be a lot smaller than n. So if we have, say, 100,000 elements in our lists, but we only have, say, 10 lists, then this log of k is going to be almost negligible, whereas this log of n is going to increase our time complexity quite significantly. So in terms of implementing this, we're going to have essentially 3 steps. We're going to have the first step, which is to build our list of iterators. We're going to have a second step, which is to put first element of each iterator into a min heap. And then our third step is going to be loop over heap, popping the smallest value and appending the next from our iterator. So let's begin. So to build our list of iterators, we're going to say iters equals, and then we're going to use the built-in function iter and say iter x for x in sorted arrays. Now this takes advantage of what is called list comprehension in Python. It's quite convenient for creating lists very concisely. Next, we're going to create our heap. So we're going to say heap equals list, because by default we need to initialize it to a list. Then we're going to enumerate our iterators. So we're going to assign an index to each iterator, and we'll say for I, it in enumerate iters. We're going to say first equals next of it. By default, this will be none. Then we're going to say if first is not none, we're going to heap push into our heap this first value, but then we're also going to append the index to it, because we do need to index our iterators somehow. Now, in order to use this heap push function, what we also need to do is import it. So we're going to say from heap queue, import heap push and heap pop. Now, with our heap created, what we want to do is we want to store our result in an array called res, and we're going to say while heap, we'll say smallest entry, smallest ID equals heap pop heap. Then we're going to check what's the iterator. We're going to say iter equals, or we'll call it it equals iters smallest ID. We're going to append our smallest entry. Then we're going to say we're going to try the same thing we did here. So we're going to try to get the next element, and then if there's a next element, we're just going to push it onto that heap. So this is really the key step where we're saving a lot of time complexity, because we know that no matter what, that's going to be the smallest value in that iterator, the smallest non-seen value in that iterator, and then we're going to put it into the heap. So if it's a very small value, it's going to be right at the top of the heap and we're going to check it the next time. If it's a really large value, it's going to be at the bottom of our heap and we're just going to check it later. So we're going to say next element equals next, and then it none. So this none, this is a default value for our next function. I'm going to say if next element is not none, we're going to say heap push into our heap, and we're going to use the same format. We're going to say next element, and then what's the ID? Well, it's just going to be the smallest ID because it's what we were using before. Now at the end, we're going to keep looping over this while we have values. So if this value is none, we're not going to push anything to our heap. But since these iterators are built out of finite arrays, we are eventually going to stop popping values from the heap and it's just going to be empty. And what's going to happen then? Well, we just return our result. So for example, when we were doing our example with this, what did we do? We started with 0, 0, 3, right? These are our iterators. So really it was a tuple. It was 0 and then 0, or 0 and 1. Then it was 0, 2, and this was 0, 0. Then what did we do? We popped the 0. We appended it to our result, so our result became 0. Then the next value in that heap value was a 6. So we put it to our heap. The min heap puts it into the back, so we're going to have a 6 and a 1. Then we're going to pop the 0, then the 0 again, and then we're going to keep going until we get the answer. Now let's test our solution using the API judge, and we pass all of our test cases in very quick time. And this is probably the best solution. There is one more solution for it, but it will give us the same time complexity, and it's not nearly as elegant. Anyways, I hope you enjoyed this video, and if you did, please make sure to like, comment, and subscribe. And if you're looking for some personalized interview help, for example, mock interviews or a personal mentorship session, then fill out our Google Docs below or come visit our site and make a Calendly appointment. Thank you for watching this video and have a great evening. Bye.